In this section, we'll make AI agents payment capable without giving them a blank check. The goal is a controlled flow. The agent prepares a transaction, shows a clear preview, asks for approval, respects limits, executes securely, and verifies the receipt afterwards. You've already built the foundations: agents that plan and use tools, blockchain and wallet basics, and assistants that can read wallet context. Now we'll extend those pieces into controlled one-chain payments with approvals, limits, and verification built in. An on-chain payment agent should never jump straight from a user request to a signed transaction. It needs a controlled lifecycle. First, interpret the intent. Who is being paid, with what asset, on which chain, and why? Next, validate the recipient, amount, fees, permissions, and risk signals. Only after a clear preview should the user approve signing. And broadcasting is not the finish line. The agent still has to confirm the receipt and prove the payment succeeded on-chain. Payment intent parsing turns a casual request into fields a transaction builder can trust. The agent identifies the recipient, amount, asset, chain, and reason, then normalizes each value into a machine-readable format. If the user says, "Send Alex 20, that is not enough. 20 what, on which network, and for what purpose? A good payment agent pauses, asks for the missing details, and proceeds only when the intent is unambiguous. With the intent clarified, the agent translates friendly language into exact on-chain values. A recipient might come from an address, ENS name, contact, or saved profile. An asset like USDC must resolve to the correct token contract on the selected network. And the chain must become a chain ID or RPC endpoint. If names collide, tokens differ by chain, or networks are unsupported, the agent should stop and ask, not guess. Before building the payment, treat the request as untrusted until it passes policy. Check the amount, asset, recipient, network, and timing against the permissions you gave the agent. If the transfer is too large, uses an unsupported token, targets an unknown address, or crosses a risky chain, block it. For higher-risk cases, require human approval. And always record the decision, so you can audit why a payment was allowed or denied. Next, the agent has to prove the payment is feasible. That means checking two balances: the asset being sent and the chain's native token used for gas. Then it estimates the network fee and compares the total requirement against what the wallet actually holds. If either balance is short, the agent should warn the user before signing, because approval without funds usually turns into a failed transaction. After validation, the agent's job is still not to spend. It builds an unsigned transaction that exactly matches the approved intent. For native payments, that includes fields like recipient, value, chain ID, gas settings, and nonce. For ERC20s, it usually prepares a transfer call against the token contract. Keeping preparation separate from signing and broadcasting creates a clear checkpoint to inspect, verify, and reject anything unexpected. Before the wallet asks for a signature, users need one last plain language checkpoint. Show exactly who receives the funds, the amount and token, the network, fees, and total cost. Then surface meaningful warnings, such as a new recipient, wrong chain, or unfamiliar contract. The confirmation should feel intentional. Approve and sign, not a vague button users click through. Human approval is the main guardrail that keeps a payment agent from becoming an automated spending machine. For high-value or unusual payments, require exact per-transaction approval. For routine activity, thresholds or trusted recipient lists can reduce friction without removing control. The key is specificity. Who gets paid, how much, when, and why. Never grant open-ended permission like handle whatever is needed, because vague authority turns convenience into financial risk. Once the user approves, the unsigned transaction moves to a protected signing boundary. That might be a hardware wallet, MPC wallet, wallet provider, or secure signing service. Private keys should never enter prompts, logs, memory, or model context. The signer returns a signed transaction, which is then broadcast through an RPC provider or SDK. At that point, the system should immediately return the transaction hash, so the user can track confirmation. A transaction hash is only the starting point. It means the network accepted the submission, not that execution succeeded. After sending, monitor the hash until it is mined and assigned a block number. Then fetch the receipt. The receipt tells you whether the EVM completed successfully or reverted, how much gas was used, and which events were emitted. Store these fields because they become the reliable audit trail for user feedback, retries, and reconciliation. Payment failures are not all the same. A user rejection should stop cleanly. An RPC timeout may require checking status, not charging again. A pending transaction needs patient updates, while a reverted transaction needs a clear failure message. The safeguard is idempotency. One unique payment ID ties together intent, signature, transaction hash, and receipt. Retry only when that ID proves the action cannot be duplicated, and always tell the user what is happening. Once an agent can move money, observability becomes part of the security model. Every payment should leave a trail: the user intent, policy checks, approval decision, transaction hash, and receipt. Monitoring can then catch patterns that policy alone may miss, like repeated failures, unusually large transfers, or first-time recipients. Keep model reasoning separated from signing keys and wallet operations. And before production, use testnets, small limits, and staged rollout so failures are contained. You now have the core pattern for payment-capable agents. Parse intent into transaction fields, validate against policy, preview the action, require approval, sign safely, and verify the receipt. Next, we'll apply this pattern to stablecoin and USDC workflows, then build toward authentication and stronger wallet-connected guardrails.